I'll begin with a word of prayer. Heavenly Father, we thank you for this day. We thank you for the weekend, complete. And I pray you help us to use this day wisely, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Amen. So I will start by letting you guys work on this example. All right? I'll give you a couple minutes. I'll be right back, okay? So try it out. I mean, here's the big hint. The denominator is what? It's x minus 1 cubed, right? So we have a denominator of x minus 1 cubed, and then you can go from there. I'll come back and solve it in just like about 2 minutes or so, okay? You try it, though, while I'm gone. I'll be right back. And then I'll take one more questions. I just want to do this example with you guys.
I skipped like 3 letters. I'm at top part of the 77. Wow. Bro, this stuff sucks, man. It really does. I'm getting 77. I think 77. I'm looking at 77 right now.
Is that partial fractions?
No, this one isn't partial fractions yet.
Is it still like trig sub?
Yeah, it's still trig sub. It's a lot of trig sub. That's it.
Yeah, I got through a lot in the next few days.
Yeah.
So I got like halfway through.
Yeah, I'm at like 54 right now.
I think it's trig sub.
Close.
Oh crap, I think he's almost back. That's how we go down the hall. He's a cool guy. I think he ran first, but yeah, yeah. We're doing this.
I'm very department.
All right. So the question is, did you know how to start the right way, right? Because if you don't know how to start the right way, you're up a creek here, right? I mean, so what should we say? We should say x squared minus 4 divided by x minus 1 cubed, right? What's the right partial fractions for this? I do a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. This is the partial fractions decomposition you want. Now, let's see if that works. So what I do is multiply by the denominator, and we get x squared minus 4 is a times x minus 1 squared plus b times x minus 1 plus c. I will call this Pac-Man. All right. So the first thing I'd like to feed Pac-Man is 1. Yeah. There you go. So that gives us 1 minus 3 is what? A times 0 squared plus b times 0 plus c. So therefore, c is minus 2.
Isn't it 1 minus 4?
Oh yeah, I don't know what I did there. Sorry about that. Yeah, let's make that c is minus 3. That would probably be better, being correct and all. Now here's a trick that I haven't showed you yet, but is especially tailor-made for this problem. When you have a repeated root, all right, especially if you have one just by itself, a nice trick is to take the derivative of the equation. So we'll take d Pac-Man dx, all right, and that will give us what? 2x equals to twice 2 times a times x minus 1 by the chain rule plus b, right? And then you can feed Pac-Man prime 1. That gives you 2 is equal to 2a times 0 plus b. Therefore, b is 2. All right, having done this trick once, we can't help but do it again. Differentiate another time. And what does it give us? Pac-Man prime prime. That gives me 2 is equal to 2a. A is 1, right? Now, if you didn't know my differentiate and evaluate trick, what would you had to do here? I mean, I hope everybody would get c equals minus 3 on the basis of examples you've already done, right? Then you could multiply it out and equate coefficients, right? You get some equations, you could solve them. But this is easier, right? This is a nice trick. Yep.
Wait, so you can only do the derivative thing if you have... If it's
You can always do the derivative thing. It just may or may not be helpful. Here, I'll try to find another one. I'll do another example. I'll show you why it's less helpful. But I should take homework questions first, so I will. Okay, so moving along here. What is our, therefore, we have what? The integral of x squared minus 4 dx over, as we learned, x minus 1 cubed is equal to the integral. What was a? 1 over, a was 1. So 1 over x minus 1 plus 2 over x minus, good grief, x minus 1 squared, and then minus 3 over x minus 1 cubed. These we can do with a u. Think about a u equals x minus 1 substitution, right? All of these can be done with that. Sorry. And so answer, right? What's answer? Answer is natural log value of x minus 1 minus 2 over x minus 1 plus 3, goodness gracious, plus 3 over 2 times x minus 1 squared, I believe, plus a constant. There you go. We hadn't done one quite like that yet, so I want to make sure I included that in our list of examples we've talked about together, because this is something that can happen, right? We have a repeated root. Yep.
Okay, how do you get the derivative of 2 equals 2a?
So go up here, right? And differentiate. So derivative of 2x is 2, right?
Oh, so, okay.
And then derivative of b is 0. Derivative of this piece just picks up the 2, yeah. Perfectly good question. Other questions? Yeah.
How did you know in the beginning to, instead of doing cx plus d, like how you sometimes do?
That is part of the partial fractions decomposition. If I have a repeated, I mean, there's two different things that can happen. If we have stuff over, x minus a to the m, the solution, the decomposition is x to the m over x minus a to the m, a2 over x minus a squared plus a1 over x minus a. Now, you say, well, why is that? Well, I just showed you that it works for this one, right? So, are there other possible decompositions? Sure. But why would I look for other possible decompositions when this one works, right? I mean, it may be the case that, let's see here, hypothetical. If we're looking at a over, let's just pick on something, x minus 1 squared plus b over x minus 1, right? Can I rewrite this as let's say a bar plus b bar times x minus 1 over x minus 1 squared, right? That's kind of what you'd like. Is it possible to do that? Like, probably. I mean, probably it is. In fact, I think a bar is equal to a, and I think b bar is equal to b. But why don't I do that? Right, our goal is eventually to integrate, and also that breaks down when I get to third order, right? Like, what's the analog of this for a cube? Because this works. I mean, I don't know what would that? I mean, I guess you could do. I guess you could do a times x minus 1 squared plus b times x minus 1 plus c, all divided by x minus 1 cubed, if that makes you feel better. But it doesn't help me integrate, right? After I did that, I'd have to undo it before I could integrate. So the goal of partial fractions is integration. So while that is true, it's not useful to me. So for a repeated linear factor, we do this. For a repeated quadratic factor, what do we do? I'll keep it simple, like x. Suppose we have x plus alpha. I'll find x minus alpha squared plus beta squared. Then if this is to the mth power, we do I don't know, a sub m plus b sub m x minus alpha over x minus alpha squared plus beta squared. And then all the way on, sorry, this is to the mth power, and then all the way down until we finally get to I'm hoping I get some new markers. My current set of markers is a little bit I'm not happy with my current black markers. Let's see here. And we're out of black markers, so it's kind of annoying. Anyway, that's what you have to put in the partial fractions decomposition if you've got 1 over a irreducible quadratic. For example, let me just be really, really specific here. If I had 1 over, just to keep things a little bit simpler, x squared plus 9 cubed, the partial fractions decomposition I'd have to go with would be something like this. A plus bx over x squared plus 9 cubed plus c plus dx over x squared plus 9 squared plus ex plus f over x squared plus 9. I can integrate all those things. Yeah. Which did I? It doesn't. It commutes. I don't know why I did it. I mean, you could go 3, 2, 1, or you can do 1, 2, 3. It's all. It's for the sake of my counting over here. I don't, there's no, addition commutes. I mean, we could go, it's not meant to make some kind of subtle point there or anything. Yep.
Can you explain the difference between just having a and a plus bx and the numerator?
You mean here?
Also in your example with the red marker, you got a plus bx there, and then the example before you just have a plus b plus c.
Right. The difference is that x squared plus 9 is not equal to 0 for all x in the reals, whereas x minus 1 cubed is equal to 0 for x equals to 1. I mean, x minus 1 is a linear factor. This is a quadratic factor, which cannot be reduced. These are algebraically different things.
So for ones that are, so that's basically how we tell if it's a plus bx or just a by itself.
Right. Here, let's look at this. This example will be helpful to you. How about this? Dx over x minus 2 squared times x squared plus 2 squared. I'm not actually going to work this out. I'm just going to set it up because working it out would eat many of our minutes. Okay? But how would you set this up? I mean, what would the partial fractions be for this thing?
Over x, subtract 2.
So I do a over x minus 2 plus b over x minus 2 squared. That picks up the first term in the denominator. Then cx plus d over x squared plus 2. And I can either square it or I can do the next one without the square. I mean, whatever. Are there other possible algebraic expressions which are equal to the integrand? Sure. Why do I prefer this one? I can integrate every last one of these things. I may not enjoy it, but I can do it. Yeah.
So you're like kind of like metaphorically unpeeling an onion, kind of.
Yes. And we're putting the onion back together.
Well, yeah, and then
Yeah. I mean, it's like I said last, like I will sometimes say, it's reverse common denominatoring. Like you're uncommon denominatoring. I can't say that anyway. Yes.
So you said it doesn't make a difference whether we put the squared value under the cx plus d or the ex plus f?
No, it's the same.
Do that subconsciously?
What, this? I don't even think about
You
it.
stayed consistent.
What's that?
You stayed consistent doing that. I'm just wondering if that's a subconscious preference.
I don't believe in the subconscious, so I don't know. But I refuse to believe that there's something you can't control that people can control in you that makes you do things. Like it goes against my way of thinking. I don't know. Like I don't believe that people watch video games or watch cartoons and then like go murder people because they can't understand the difference between reality and cartoons. So I don't buy it. I think they're evil people and they did it on purpose. And or they took a sleeping pill, which makes you go crazy. So I don't know, one of the two. It does seem like sleeping pills have something to do with it. In the fine print of every one of these stories, there's like, recently started taking, you pick your favorite sleeping pill, but, you know, yeah.
So I know, I didn't
Sorry.
understand how the denominators work, but now I do. But where
Yeah.
does the x come from in cx plus 3?
Well, let's see here. How could I explain this otherwise? I don't know what to tell you. This is the partial fractions decomposition. I mean, I can't say this any other way. I don't have something to tell you. I'm sorry. It's not in me today. I would like to tell you something else, but it's because this is x squared plus 2, as opposed to x minus 2 squared.
Okay, so when there's
These-
an x squared, there's an x up above.
Yes. Right. Yeah. Yes, sir.
So like when there's a quadratic in the denominator, we have to write a linear something in the numerator for the preceding.
Yes. Yeah.
And if it was something more,
Guys,
then if it was like something like
here, let's try this. If I have I don't even know how I can get back to that. I mean, I guess the only thing I can really tell you guys is the only way I can really give you an explanation is to do something like this. So x squared plus a squared, right? How does this factor? This is something like 1 over x minus ia times x plus ia, right? So if you believe in partial fractions working for complex factors, this would be a over x minus ia plus b over, you're like, great, you're explaining something I don't understand with something I don't understand even more. Good job. But just hang with me for a second here. Suppose you admit that whatever we're doing in the reals should also make sense for complex, then we'd have this, right? But what happens when you put this back together? Let me put something else up here like 3x plus 2, just to be random. I mean, what would happen with this? How do you make a common denominator here?
Multiply by.
Right? Let's see here. Oh, yes. I mean, so you see the pattern. When you combine two things like this, you get x, another term, and x squared plus a squared downstairs. So you can see where the x term is coming from if you're willing to take a complex variables approach. There may be some example I can give you which would convince you. I just don't know it at the moment off the top of my head. Now, you had a question that was invariably not the... Because I've been asked this, like this is about this, that was like the 4th time today I've been asked that question, I think. I mean, I'm not counting, something like that, but yeah, which is fine. It's an important question to ask. That's the question you all must ask, all right? And either come to understanding or acceptance that the x has to go there, yeah.
If the x was cubed, would it be like over? What would be on top of it?
So suppose we had x cubed over x squared plus 2.
No, like it was like x cubed plus 2.
Oh, x cubed plus 2 downstairs. Ooh. Ooh, and then numerator whatever you want, right? Stuff you don't really care. Yeah. So, yeah, so what's the thing about a cubic? Any real cubic, what can we say about it? It's an odd function, right? If you graph it, which means it crosses the x-axis somewhere, right? So there exists c in the reals such that f of c is equal to 0 for f of x equal to x cubed plus, ax squared plus bx plus, I already used, so d, okay? I mean, there is always a 0 to a cubic. So that means that the factor theorem says that you can factor that out, right? And then there's going to be x squared. So any cubic will always be factored into a quadratic times a linear term, and the quadratic may or may not split. Now, x cubed plus 2 is relatively benign, sort of. I mean, what is x cubed plus 2 can be equals to 0. What do I do? Take the cube root of both sides, right? Which is, by the way, minus the cube root of 2. So x cubed plus 2 is equal to x minus the cube root of 2. And then x squared. Yeah, that one's for free. And then the suffering. So then you got something, let's say b, x, and then plus c. And now what are b and c? It's ugly. But you could figure it out because this has to multiply out to give that, right? So you could actually figure out what the b and c must be, at which point you're going to be able to tell whether that is a quadratic which can be factored or not. How do you tell whether a quadratic can be factored or not? I feel like I said, I think I had a quack in there somehow. I don't know how that happened, but you guys tell me. So I have ax squared plus bx plus c. When can I factor it? What simple thing can you check? See if what? I just didn't hear you. I'm sorry.
Can't you like see if it adds and multiplies?
Adds and multiplies. Oh, you're thinking about integer factors, but we also allow for real numbers.
Isn't it when you determine the quadratic formula is a perfect square?
When the quadratic formula is a perfect square.
So-
I think you guys are still thinking about integers, right? I mean, my question is when can this be written as like a times x minus, say, r1 times x minus r2? How do you find r1 and r2? I may not be disagreeing with you. I'm not sure yet.
Doesn't it multiply to c and add to the b?
Is that what you're saying? So you're saying c is equal to r1 plus r1 times r2. Fine. But like you give me a number. 3 is 3 times 1. It's also 15 times 1/5. So what does that say to me about? I mean, like that alone, that c is the product of two numbers. Like
Are we still going with there exists c as an element of reals? Like, what's the application of that?
What I'm trying to get at here is suppose you have this problem, right? I'm not convinced you guys actually know how to tell whether or not. I mean, I keep getting asked questions today that suggest to me that you do not understand the difference between a quadratic, not saying anyone in particular, but just generally, it's in the air. I'm not convinced that you guys understand the difference between a quadratic which can be factored and a quadratic which cannot be factored over the reals.
What about primes? This can be
An irreducible quadratic is, let me just say the answer. Fix this. All right, so there are three cases, right? Graphically. You got this one, the one we like. You got this one, which we like more because it bounces. And then, of course, you got, and I'm assuming that we're looking at expressions of the form, essentially ax squared plus bx plus c with, these are y equals that, with what? A positive, right? So this, we have r1 and we have r2. Those are the zeros of the quadratic, right? This one just has r. So here we're looking at y is a times x minus r1 times x minus r2. It factored over the reals. Here we have y is equal to a times x minus r squared. It bounced, right? And then over here we have y is equal to ax squared plus bx plus c. I mean, you can't factor it. If you like, you could complete the square on it. I'll leave that a out there. B squared, stink, c minus 4b over 4. I still did it wrong. I'll get this right eventually. What should I put here? So I've added a b squared over 4. So I should say like 4c minus b squared divided by 4. I'm sorry. Can I just, for the sake of simplicity here and not having to change all of this, can I just erase the a for just our discussion here. Because otherwise I got to divide by a and blah, 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 blah. Okay? There. If you set the coefficient of x to 1, that's completing the square. So if you complete the square on a quadratic, you can tell it's irreducible by what? You end up with something squared plus this, right? In other words, what? 4c minus b squared is what? Greater than 0, right? So let me just, in all cases, we have that x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? In fact, this x is either giving me r1, r2, or the r that I wrote there. Or if b squared minus 4ac is less than 0, this condition says that ax squared plus bx plus c is what? Irreducible. It cannot be factored over the reals. The reason I'm talking about all this, you asked me about x cubed plus 2, right? Now, it's a pain to find the b and c here, but I kind of have an intuition. In fact, I know that this will be an irreducible quadratic for this problem. Part of the reason I know that is if this was not an irreducible quadratic, there would be other real zeros to this equation, x cubed plus 2 equal to 0, but I know they're not. I happen to know the other two solutions of this equation are complex. They involve third roots of unity, whatever that is. But the point is, this will be, I mean, when you actually work out the details, this will be one of those irreducible quadratics. This is the difference. So these are, linear factors. This is an irreducible factor, and the algebra works out different for these different cases. You guys know this already, yes? Right? No?
Expressed in that way.
Not expressed in that way. Okay. But this matters. There's a really big difference between that and that. Yes?
I knew that. I can't remember what b squared minus 4ac is called. Like, there's a term.
Oh, yes.
I just don't remember.
Fair enough. Yeah, that's called the discriminant. Because it discriminates what kind of case you're in, right? All right, someone here must have a homework question. Save me from my algebra review. Yeah, you guys are like, no, we're done. Let's just pack up our bags. We'll come back for the, oh, you got one? Okay.
Yeah, could we look at number 82, which is equal to number 90?
Uh-oh, number 90. That sounds hard.
I'm just not sure where to begin on it. It seems easy enough, though.
8.3, number 90, huh?
Yes, 8.3, number 90.
By the way, guys, lest I walk away from this discussion without making another point, you can always tell what case you're in by completing the square, right? If you try to complete the square on one of these guys or one of these guys, it still works. Completing the square on one that bounces, well, it's like square completed. It's just that, right? You complete the square on something like this, is this. If you complete the square on something that factors, what happens? Let's do it. What happens like x squared plus 4x plus 3? This factors into x plus 1 times x plus 3, right? Complete the square on this, what happens? We have x plus 2 squared, right? Minus 4 plus 3, also known as x plus 2 squared minus 1. So if you complete the square on something that factors over the reals, you just end up with a minus here instead of a plus, which means that you can then look at it as the difference of perfect squares and factor it. You know? Which, of course, is what we expected, because we know how to factor. But completing the squares is a general method. It will always reveal the true nature of the quadratic to you. If you don't know how to complete the square, it is definitely worth your time. All right, number 90 is like way harder than this, though.
For example,
Yeah, I mean, you can do it, but it's 6 equations and 6 unknowns, and this, right, this is a hard problem. This is a pretty difficult problem. Because these are strongly, I mean, probably that differentiation trick I showed you be helpful. Yeah. This is just an unpleasant problem. I mean, if you plug in 2i, you can try complex arithmetic, makes nice things happen. But yeah, I think I can get A and B without too much trouble, but past that, yeah. It was number 90, right?
Yeah.
Let me see here. Oh, this is a neat problem. So the following sum is a so-called finite Fourier series. F of x, sum, that one, right?
Yes.
I equals 1 to n of a sub I sine of x. In other words, that's equal to like a1, oh, that's the sine of ix, actually. Sine of x. So a1 sine of x plus a2 sine of 2x plus a3 sine of 3x, right? This is what that summation means. And finally, an sine of nx. Okay, so this is a so-called finite Fourier series. And we're supposed to show, using exercise 89, that the nth coefficient of a sub n is given by, so we want to show, and this is little n. So let me use something else. Let me say that we want to show that the kth coefficient is equal to 1 over pi, the integral from minus pi to pi of f of x sine of kx dx. And then he asks us to find it for a specific one.
So problem 89 in this set was assigned as well, and I understood 89. I just don't know how to apply that number 89 to this number 90.
Yeah. What 89 tell us? We're supposed to show that sine. Oh, so we've already shown that sine is orthogonal.
Sine and cosine.
Sine and cosine are orthogonal. Yowzers. So let me just, number 89, you have shown that, for example, sine of kx with sine of jx, which is, by the way, defined to be what? The integral from a to b. So for our context, it would be from minus pi to pi, right? Of sine kx, sine jx, dx. What was that worked out? That worked out to be what?
Just 0, right?
Usually 0. 0 if k is not equal to j. But what happens if k is equal to j? Yeah, they just deal with the case of distinct functions, but you could also have the case where k is equal to j. What would this integral become when k is equal to j here?
Sine squared.
Yeah. We'll keep the k, sine squared kx dx, which is what? Minus pi to pi, 1/2, 1 minus the cosine of 2kx dx, right? Yep.
Out of curiosity, what would the dot product of that look like? Because, like, I thought that if it zeroed out and if it was like orthogonal, then because like.
Oh, this is the generalization of a dot product to functions. So sine and cosine are kind of like I hat and j hat for functions. They're independent. They're perpendicular in function space.
So they're orthogonal
Yeah,
by definition.
by this calculation. The other part of the problem is with sine and cosine. But sine of different arguments are also orthogonal. Like sine of x is perpendicular to sine of 2x. But
Orthogonal.
perpendicular. I mean, it means that the definition of it for these functions is that this integral works out to 0. So when these are distinct, when j is not equal to k 89, you calculate this integral and you get 0. But if k equals to j, what happens? This piece goes to 0 because it's the sine. This integrates to sine, which evaluates to 0 between minus pi and pi. So all that remains is this x over 2 evaluated from minus pi to pi, also known as pi. So it's actually pi if k is equal to j. So this, I mean, if you want me to chase this rabbit, I'll do it. The length, if you will, of sine of kx is the square root of pi. If you take the dot product of a vector with itself and you find that the answer is 7, that means that the vector has length square root of 7. If you've had physics, you know that. If you haven't, there's no point in us having this conversation. This is problem 89. I'm helping you with problem 89 and 90. I'm not trying to explain all of calculus 3 here. So let me just behave. The point is that if we take k equals j, it's pi. Okay. So with that in mind, you calculate f of x, comma, sine of kx, right? And what that is the integral from minus pi to pi of f of x, well, f of x sine of kx, right? But what is f of x? We're given that that is the sum, right? I equals 1 to n of a sub I sine of ix sine of kx dx. But the integral is linear, right? So we can pull the sum out. The integral of the sum is sum of the integrals. And you see what we have. And this is a constant. So I can pull that out. So I have integral from minus pi to pi of sine of ix times the sine of kx dx. But what did we just get done saying? We said that the integral of that product of sines from problem 89 and also the little bit I just did for you for free right here, right? So this is what? This is 0 if I is not equal to k, and it's pi if I is equal to k. So you have the sum of n things, right? But only one of those things counts. They're all 0, except for what? Except for the kth one. And the kth one gives me a sub k times pi. Yep.
Are you saying that is f of x that second thing there, the sum, that sum right there is if f of x is composed of sine of kx?
Not multiplied.
Oh, it's multiplied.
Right. So f of x is given to be that in problem 90. It says this is told to us in problem 90. Yeah. So I'm just plugging in that. And 89 basically told me, hey, if you integrate sine times sine, you get 0 usually, except for when you don't, which is exactly the kth one, which produces the pi. But then, of course, what is this? This is, well, I'm sorry, I don't need to do anything else. I mean, right here. So you just compare these two expressions and solve for a sub k. You get a sub k as 1 over pi, integral from minus pi to pi of f of x sine of kx dx. if you tried this problem before, what I'm doing will be helpful. If you haven't, I'm going entirely too fast, but I'm helping on the basis like you've already played with it already. If you haven't played with it already, then I'm sorry, but you know. Listen, so this is an interesting problem because what it says is that if you have a function which can be built from a sum of sines, you can calculate the coefficients for the sines by doing these integrals, right? So it says essentially this integral, right, will tell me what these things have to be. So the coefficients of this expansion of sines has to do with integration. And then like part B, you actually calculate the first couple of coefficients for f of x equals to x, right? Now logically this is kind of bad because you have f of x equals to x. Can you write this as a finite sum of sines? No, it's not possible. But if you study what are called Fourier series just do this. You just keep going and going, and the formula you derived is still true. It's called the Fourier Coefficient. And so if you do part B, x looks like this, guys. So minus pi. So like the sign would be something like, I don't know, it's like that. Maybe that's the first thing. Oh, I can't do math. What's sine of x? What's sine of pi? I'm an idiot. So, yeah, sine pi is 0 and sine of minus pi is 0, right? But then when you add in the sine of 2x, it gets a little bit better. And when you add in the sine of 3x term, it gets a little bit better still. And I'm not doing it justice, but as you go on and on and on, it gets closer and closer to, it gets closer and closer to mimicking x by adding together sines. This is what MP3s are built on. You take a music and you can decompose it into its notes, its fundamental frequencies. This is Fourier decomposition. That's what this is. I mean, these are different frequencies of the signal, and you're breaking the signal up into its fundamental frequencies. That's Fourier analysis. But it's also integrals of products of sines, which for some reason gets less respect. I don't know. Funny. Anyway, if you have other homework questions, they're still tomorrow. Don't worry. Thanks, guys. Sorry if I've insulted you with this algebra. Not my intention. Yeah.
Can I set it to the for office hours tomorrow? Do you have any time available tomorrow during office hours?
Oh, yeah. I mean.